Welcome to this tutorial at the first day of the SWOT for SCLS conference. My name is Ammar, and I am a PhD candidate at the Department of Bioinformatics at Maastricht University in my last day. So I will be the main facilitator of this tutorial, along with Igor Willihagen, who will join us later after the break. We are both working at the Department of Bioinformatics, and this tutorial, titled Life Sciences Knowledge Graph Constructions with More Semantics and Less Code, will walk you through the process of creating knowledge graphs, semantic knowledge graphs, from data sets that are expressed in tabular formats like CSV or TSV. And the words here, more semantics and less code, it's mainly because the semantic web in general has a steep learning curve, and I've been working in this field for 5 years, and I always see people struggling to get into the point where they can go through the whole pipeline from the data set into the semantic knowledge graph. And using a specific set of technologies, we are trying through this tutorial to lower this barrier and make it easier to tap into the semantic web for life sciences. So there are two things at the beginning. So there is a GitHub repository. This is for the second half of the tutorial. So this is the link and the QR code. You can follow. You can already check that. There is some requirements, as you've seen in the abstract of the tutorial. You need to have Docker software already installed on your computers. We have half an hour break. If you didn't do that, it's fine. You can do that later. And I think you all received Slack invitation. So Slack is also communication software. It will be the main channel of communication for this tutorial. There is already a channel in the Slack workspace called SWOT for SCLS T2 Constructing. This is the one dedicated for this tutorial. We're gonna need this. In the first half of this tutorial, I'm gonna introduce linked data, RDF, SparkQL. I'm gonna clarify those terms. Those are the building blocks of the semantic web, and we're gonna learn the SparkQL query language. And in the second part, we were gonna work on that platform called Linked Pipes ETL, which is used to construct knowledge graphs. So I'm gonna start with the most basic thing, which is the traditional way of representing data in life sciences, which is tables or Excel sheets or any format, any table format. This is a classical way of outputting data from experiments, especially wet lab experiments. This is an example of, for example, a toxicity assay data set where you have nanomaterials here in this case with specific properties, and then you have the assay with the cell line, species, the time, the dose, and the toxicity or the cell viability. So this is a typical kind of data set where you want to test a specific set of materials in a cell line with a certain concentrations and doses and time points, and to check the viability. So there are 4 important things to notice about this type of data presentations. The first is the model of this data, which is a table. It's the basic form, the table composed of rows, columns, and cells. So there is already a semantic meaning for this kind of representation, because usually the row represents a sample in your data set or an instance or an assay that you're working with. The column is actually the model of your data. So the column are all these attributes that you have measured and reported in your data set. And the cell are the actual values, are the content of your data for a specific sample at specific column. The second thing is the type of storage for this kind of data. This data is represented as a flat file. We call it flat file. It's a file stored on your operating system, and it has different formats. So this is the third attribute of this representation. So the common file formats are CSV, comma-separated values, TSV, tab-separated values, and Excel or XLSX, like this image here. So it's a tabular model with a flat file storage, and 3 common data formats or file formats. The fourth characteristics to notice is how do we interact with this tabular format to query or to filter. Usually, since those are textual files, you need an external software to load those files into, or programming language where you can interact with it. And to query and filter this data, you usually either we use Excel, Google Sheets, or a programming language of your choice. If you are a Python programmer, you may use Pandas package to load this CSV and interact with it, or our data frames. So this is a traditional way and very common way of representing data. But there are issues with this, or limitations with this tabular data format. The first thing is the different formats, different file formats. So you need specific packages to read and parse every type of these formats, so they are not interoperable. There is no piece of software that can interact or manipulate these data sets, whatever they are, because they have different file formats. The second thing is they're not directly queryable. You need an external software, and you need specific set of skills to interact with this data and query it, like either Microsoft Excel or programming language, etc. The third limitation is heterogeneity in nature. So as we said before, the model in this data in these files are the columns, right? You report specific attributes, and those attributes are based either on protocol you use in the lab or a specific minimum reporting standards. So they are heterogeneous, so you cannot combine easily two files together if you want to, for example, make a more increase the number of instances you have to create more statistical power, or just to explore the data. So this is also a limitation. Several standards and conventions. This is also related to what we said, because you follow a certain protocol or certain minimum reporting standard that require reporting different things. The lack of semantics and interlinking. Also, because of the flat file nature of this data, you cannot link them together. You need to load them somewhere else, and you need to manually map the columns to each other to make sense of them. Redundancy is also another common thing. So if you see in this example, if you have an experiment where you want to test a material against a cell line, or a small molecule against a protein, but you need to test different concentrations at different time points, the whole at each row, the whole information are repeated, and each time you only change the dose and the output of the assay. So you see there is a lot of redundancy. All this information about the material here and the characteristics of it are repeated, and every time we change the value of 2 columns at a time. So redundancy and this repetition is also one of the things to pay attention to with tabular data. And the last and the most important thing is the implicit knowledge. So in this data set, for example, there are a lot of implicit knowledge. Like the row number, it's something you know that this is a sample in my experiment, right? But it's not written anywhere in the file, in the CSV file. This is something you know. This is an assay sample, the meaning of the row. For the file itself, you know this is an experiment I ran at specific day or at specific year for a specific project, right? And I published in a specific journal, but none of this information are encoded inside the CSV file. You already know that. This is the knowledge you know. It's implicit. Nobody else can figure that out. And even yourself, a year or 2 or months later, you will forget about it. So when you come back to this file, like, I don't know what this means. I don't know what the name of the file means. I don't know where did I put it. And all these issues because of this implicit knowledge that is not inside the file. And we call this information metadata, that is not stored with the file, but you know it yourself. So, which makes this data hardly reusable and hardly interoperable. And if you're familiar with the FAIR principles, it's a term, an acronym of 4 words: findable, accessible, interoperable, and reusable. It gained a lot of popularity since 2016, because of this issue that most of the research output, especially the experimental research, is not reusable. We cannot reuse experiment results from previous publications and build on them because of this data, of this issue that we cannot find the data, we cannot access it, we cannot reanalyze it, and we cannot reuse it. So we want the aim of this, like the whole approach or the whole way of thinking, is that we want to look for new alternative of data representation that allows us to integrate data, to query it, explore it, and most importantly, reuse it. This takes us to the concept linked data. So linked data is not something was made initially for scientific data to be expressed. It dates earlier than that. So it's a set of design principles to share machine readable data on the web. So it was basically invented to serve the World Wide Web. And the idea of it was to move from a web of linked documents to web of linked data. So all the internet is about URLs. You go to your browser, you go to your URL, you access a resource, it's a website. Inside every page you have links to other websites and to other pages. So it's already linked documents or linked web pages. Linked data was aiming to make those web pages, the information inside of them are machine readable. So if you have a name of an author in a web page, you can really tell that this piece of text is an author and this piece of text is a date and so on. So the linked data was initially made to convert the textual documents of the internet into more machine readable and understandable data, like encoding them as entities, people, dates, subjects, media, and any kind of representation. And then this kind of approach was transferred to another disciplines and fields because this model is very general and it can be generalized to encode other types of data like scientific data. The value of this approach, there are several dimensions for that. The first of them is data integration, because we encode the data as a graph. As you see here, it's a set of nodes and links between them. This is a very general representation format. You can encode any data using this approach. So this is an added value of adopting linked data. The second valuable thing is interoperability, because this representation format is encoded in a data formats that can be read by the machines and that can be converted from one format into another. It's not the same problem with CSV, TSV, and Excel sheets. Other things are by adopting data standards, we can increase the quality of the data. I will come later to that. And accessible to humans and machines, because this data is parsable by the machine and can be manipulated without the human interaction. And the last thing is exploration and analysis. This nature of the graph allows us to find patterns inside the graph that is not possible to do it in a table. So if you see in this example to the left, we have a node in this graph, and this node represents a person, that person called Bob. And then we have another node that represents an art, and that art is called the Mona Lisa. It's the Mona Lisa painting. And we have a relation between the person Bob and the piece of art Mona Lisa called is interested in. So we have two different entities that are different in nature, and they have a link between them. The same here, we have another entity of the same type of Bob. It's a person called Alice. And then we have a relation that Bob is a friend of Alice. So we have very different kind of information encoded here. We have relationships between people, and we have interests between people and art. And also we have here, Bob is born on. So we're not only connecting entities to entities, but also we're storing attributes of those entities. So we have recorded information about Bob, like the date of birth in this example. Or for the Mona Lisa, it's the created by, was created by, so also linking information about the piece of art, who made that piece of art. This is very basic and simple example showing us that in a graph structure, we can encode different types of knowledge. So this is the aspect of data integration. That means we can, for example, link data about a toxicity assay with the data about transcriptomics or data about other types of omics and so on. So we can connect multiple types of data using this graph structure. Since this term coined and this set of technologies launched, many initiatives and institutions and people started converting their data sets into linked data formats and put them on the internet. So they are findable, accessible, interoperable, and reusable. And this has created what is called the linked open data, LOD. I think, yeah, there is a link here, but yeah, this is LOD-cloud.net. This is the website where they gives information or gives you access to all these data sets from different disciplines. So you see here they are colored, some of them about geography, some of them about governmental data sets, life sciences. You see the biggest part of this network is life sciences data sets, linguistics, media, publications, social networks, and some user data sets. So this is being adopted more and more, and you can see by making your data available in this graph format, you can also link to other data sets from other domains, which allows for big opportunities for exploration and analysis. So now we're talking about the graph as very abstract structure, right? But if we want to make it physical data set, we need a framework to go from the table to the actual linked data format. And this framework called RDF. RDF is an acronym of Resource Description Framework. And it's a standard developed by the W3C, the World Wide Web Consortium, to model, it's a model for data interchange on the web. As I said before, this is all linked to the web because it was initially developed to make the internet machine readable and expressed in a semantic way. So RDF is the framework that allows us to express data in a graph structure, similar to the example I showed before. And the main use cases of RDF is to use as a data interchange format or language that is more flexible than XML or SQL, and also to link large data sets together and publish them to the internet, as you saw in this example. Please, you can stop me at any time if you have any questions. I'm deliberately being slow here because I want to clarify these terms very clearly because this will make it easier for the later sections. So RDF is the framework that allows us to go from this abstract graph model into real files, real formats that we can interact with, we can store, and we can publish. And the way of doing this is by deconstructing this graph into simple elements. The element is called a triple. And the triple is composed of three pieces: subject, predicate, object. This is derived from our way of communications, from the natural language. When you make sentences, the sentence contains a subject, contains a verb, and contains an object, right? So the origin of it is the natural language of communication. And RDF is adopting this triple concept as a main way of representing data. So here the subject could be Bob, as we saw before. The predicate could be was born in, and then the object is the location, the city, or was born on, then the date, right? So any statement in life with this model, any statement in life, scientific or not scientific, in any discipline, can be represented as subject, predicate, object. But now we want to see how in a computer, how electronically we need to encode those statements in a way that the computers can parse and understand. And here I want to clarify a couple of acronyms that we see a lot. So I think the most common one, and everyone is familiar with, is called URL. Whenever you want to enter anything on the internet, they tell you type this URL, visit this URL, right? So URL it's an address. It's the easiest way to describe it. It's an address to a resource available on the internet that you need to access it and get the information from it. So the smaller subset, it's another term called URN, which the URL should be accessible through the internet. You should go to the browser and you put the URL in there and you're able to retrieve a document and access it. The URN has the similar semantics, but it's only a unique name and not a resource. So the URN could be the identifier of a book. That's something like the ISBN here. It's a URN of a book. It's not something you can access on the internet, right? But you need to go to the library to ask for a book with that specific ISBN. The URL is the same. It's a unique identifier. It's a unique name, but you access through the internet. The URI, as you see from this image, it's a bigger subset. It's a parent of both of those groups, and it's a unique resource. Also, it's unique, and it's able to identify a resource regardless if it's available on the internet by its location or by its name. So the URI is a generalization of both the URL and the URN. Then the concept IRI came, which is the I for internationalized. That means URIs, usually you use the English language, the ASCII characters from A to Z and some of the symbols to express those, like as you see here in this example. So no, I don't want to go into it. But this is an example of a URL, and because the URL is a subset of a URI, that makes it also URI, and because of URI is a subset of IRI, that means those are both URLs, URIs, and IRIs. The IRI is more broad because you can basically represent any resource with any language, with any set of characters. It's not specific to the English characters. So why I'm bringing this up? I'm bringing this up to talk about how to represent this triple concept in a computer. So the way RDF does that is by encoding anything in the subject should be represented as an IRI. And because the IRI is bigger than the URI, that means it can be also URI. And because the URI is the parent of the URL, that means it can also be URL. And you put that URL between two pointy brackets. So any entity you want to encode in RDF format, it has to be expressed in IRI format, right? That means you need to generate for your entities unique identifiers and to be expressed in this format. The same for the predicate. The predicate also has to be an IRI. The object, it has two cases. It can either be an IRI or a literal. A literal, I will come to that later. That means it could be a text, a string, it could be a number, or it could be a date, and so on. Those are called literals. So if we go back to this simple graph, in RDF format, Bob could be, for example, the LinkedIn profile of the URL of the LinkedIn profile, or the URL of the Facebook profile, or any generated address. But if it's not accessible on the internet, then it's not a URL anymore. It's a URI because it's not a location on the internet, but it's a unique name only, right? So here in this example, when the Bob is interested in the Mona Lisa, both Bob and the Mona Lisa are IRIs because they are entities, they are resources. But here, Bob is born in a specific date. The object here is literal, right? So Bob is the IRI, is born, is the predicate, also an IRI, but this is literal. So it doesn't point us to anywhere. It is a date value. So this is the simplest way of representing knowledge within the RDF framework. And you can imagine every time the graph is a set of triples. So every time you add another triple to the graph, you extend it in a way. So here, if we start our graph with one triple, which is Bob is interested in the Mona Lisa, and then we added another triple, says Bob is born in this date, then it automatically, there is no redundancy here because the IRI of Bob is unique and it was already there in the graph. So when we add a new triple, only the predicate and the object of the new triple are added. The third time we add another triple called Bob is a friend of Alice. Bob was already there. It's unique IRI. So only the predicate and the object are added. And this way the graph is built block by block or triple by triple, and it will expand. And it will be connected because everything is unique. Every entity is unique. So all these entities will be connected with each other, and then we will able to make a queries and ask about them. So yeah, this is, as I said before, this is the structure of the subject or the predicate and the object. It's an IRI within pointy brackets, and there are some, as I said before, linked data is a set of best practices or design principles to make data available in RDF, and these rules are to use IRIs or URIs for names or things. We already talked about that. The second thing is to use the HTTP URIs. That means URLs that people can access because people can look up, because the resource is more useful if you can go visit it and see what information it provides, right? If we generated a URI for something doesn't exist on the internet, then we are only limited to whatever information linked to that resource. So this is a recommendation or rules for linked data, but it's not mandatory to have, as we will see later. This was recommended for the web, but when we work with our own data sets in life sciences, for example, this is not possible to do all the time. Also, the last one is to include links to other URIs. That's what I said before. The more you link your triples or your entities together, the more information you reveal and the more patterns you can extract with the query language. Going back to this to the statement or the triple statement, as you saw, if I need to every time write the entire URL and only change part of it. So, for example, if we're having a Facebook profile or LinkedIn, always it will start with https www.facebook.com/user/ then the identifier of the user. So the RDF framework, they figured out a way. What if I can define a prefix or an acronym, an abbreviated way of the biggest part of the URL or the IRI, and then I can reuse it later in my data. So we do that by using the word prefix, choosing whatever prefix you want to use, and then put the static part of the URL or the URI that will stay the same. So here, for example, we have a URI for a drug entity, and this is available on the internet, for example, and every drug has a unique identifier is changing here, but the remaining of the URL is not changing, right? This is a URL for a drug on the Bio to RDF knowledge graph. And the way we can make it easier to deal with is by defining a prefix. We call it a drug bank. We put all the fixed part or the static part of the URL, and then we can reuse it by mentioning only the acronym and then put the changing part of the URL, right? So if we added another drug to our graph that called, for example, DC9991, we can the same way we say drug bank and then colon DC9991. We don't have to repeat the entire thing again. So here's another example for a full triple. So we defined two prefixes because we have two formats of the URIs. One to represent the entities, that's called bio2rdf.org/drugbank, and the other one to represent other things like the relations, the predicates, and we call it bio2rdf.org/drugbank vocabulary. And the triple in this case will be drug bank, the identifier of the drug. This is the subject, the predicate. This is the easiest predicate in the RDF framework is called A, and it's a synonym of RDF type. As you see here, RDF is also an acronym. That means there is a URL behind it, and a type is the name of the predicate. So it already encodes the semantics. That means we're saying the subject is a type of something else, right? And on the right side, the object is also an IRI or URI because it has a prefixed URI and then the name drug. That means this entity called DB0001 has a type, RDF type, or is a drug, right? So this is a triple. Every time you add another triple to your graph, when you say, for example, DP402 is a drug was already there in the graph, so we will draw only the subject and the predicate, so we will have two drugs with two A's linking to the same entity called a drug. So try to familiarize yourself with this concept. This is comes a lot. This is the heart of the graph and the knowledge graphs. We said before also the object can be either a URI or a literal, and literals in RDF are like strings because you're gonna write that in the file. So it's a piece of text. You put them between quotations, but then you need to tag them with their own data type. And the way you specify the type of this piece of string is by using the symbol hat twice, and then you mention the data type of that value. And the data types themselves are also IRIs. They are also unique entities coming from this prefix, and we have specific entity for date, time, integer, double, boolean, and the string. So this number 125, if it appeared in any file, in a CSV or on the internet, all the softwares treat them as text, right? It doesn't distinguish between 125, this is numeric or this is not. But in RDF, the moment you tag this piece of text with XSD integer, that means all the software using it will know this is pointing to a number. True, also it's also a piece of text, but you will say it's a boolean. That means it's a false statement or true statement about something. This is how we're adding up the semantics to the actual text. So a CSV or an Excel table, everything inside of it, if I go back to the first, like here, a computer will never tell that this is a number that refer to the core size of this material. This is only the human can understand that, but the machine will never be able to infer this relation from a single line in or a couple of lines in the CSV, right? Here there is a model. The model is AlTO3. This is aluminum oxide. Is a material. So you can see how we can convert the CSV piece by piece into a graph. Every value in the column material can be encoded as a triple. The material, this instance, the material aluminum oxide is a material, right? And then aluminum oxide has a core size of this value. Subject, predicate, the course size, and the value, right? So this is where we have the semantic meaning. So we're including the column names as predicates inside this graph. So I will come back to later to this, but I was just showing that the literals also have semantic meaning, and by using those, we can distinguish between what is text and what is number and what is date and so on. Is everything clear for now? So another example to build on that. So before we used the drug, like identifier for drug or URI for drug, and we used the predicate A or RDF type to link it to a class to say that this URI is a drug. Here I'm applying that on literals, and we are saying again, this identifier or this URI has a label, paracetamol. So now with one piece of triple, we only knew that that resource, that URL was a drug. It's a member of the class drug, but we didn't know which drug. We added another triple to the graph saying that same resource has a label or labeled as paracetamol. So now with two statements, we know that the resource is a drug and it's called paracetamol at the same time. So a third triple where we're using the term weight, I'm referring here to molecular weight of that chemical entity, and I'm saying here 20. So we know that this is wrong, like there is no chemical information here, but just to show you that an example of using a number with integer. And because weight is something linked, we know that weight, it should be expressed as a number. So here you can semantically tell that the weight, the object of any triple with the weight as a predicate should always be a number, right? But when you have that as a 3 columns in a CSV, all of them will be pieces of text. But here, this is not a text. This is a node. This is an entity. It has a unique URI, and it's linked to other pieces of information, like a label, weight, or even a type. So using this simple concept, we can convert anything into semantic statements. Anything you want, I can, for example, give this mobile http and then swat for hcls.org, then /2024/mobile/1. This is URL or URI that is unique, and that represents a mobile with identifier 1, because you make your own identifiers, you make these URIs. Then a second mobile will be called /2, /3, /4, and so on. And then when I say in a triple, this resource is of type mobile, then I already give it a type. Then I give it a year of manufacturing. Here, instead of weight, it should be year of manufacturing. It could be password. It could be like email, right? You can link anything to this resource. You can give it label or the owner, and you can start making those triples to link to provide more information about this resource that you created in the first place. So now we have this data from multiple sources. We encoded them as a set of triples. Those triples aggregately become a bigger graph. I need a way to traverse this graph. I need a way to find patterns, to find answers to my questions or to my queries. And this is where the third component in the semantic web was built, and it's called SparkQL. It's a query language to query those RDF graphs. So with this big graph, for example, let's get back to this simple. Here, if I have this graph and I want to ask a question, give me all the friends of a person that likes the Mona Lisa. I want to have this question, but this is simple because I have only 2 people here, Alice and Bob. But when I have a million people, of like billion people on Facebook, and 5 of them already mentioned the Mona Lisa somewhere. Facebook want to know, give me all the friends of the people who mentioned the Mona Lisa in the last 5 days, or the people who went to this conference in the last week. So they can tell all our network of friends, all the friends, that someone of them visited SWOT for HCLS, the 2024 version. And you need to be able to ask this question to the graph where it contains millions of triples inside of it. And for that, this language of querying called SparkQL, it's an acronym that for SparkQL protocol and RDF query language. So this is a query language to ask questions on this graph. And this is the important thing that we want to learn in this part of this tutorial, because everything I'm talking now are concepts. There is no technical things here except how do we encode the triples in the computer. So if you are familiar with relational databases and their query language called SQL or SQL, SparkQL is the SQL for RDF. So summarizing, we have 3 pieces of components to achieve to say that we have semantic knowledge graphs. The first thing is the data model, which is the data representation format, which is RDF, and the triple concept, the data model, and this is how do we structure our graph, how do we align it, how do we link it, and then we have the data store. Where do we want to store these RDF files? We need to put them in some sort of database that we can later query them, right? And this is called the triple store. There are many vendors in the market providing those software where you can deposit your RDF data, Blazograph, GraphDB, Stardog, Jena, Virtuoso, and so on. I'm not sure if you heard of any of them, but they are vendors like Microsoft Excel, right? Google Sheet, like Python, right? They are vendors who created the software where you put your RDF data in and then you can do things with it. And the third component is the query language. In this case, it's called SparkQL, and Sparkle. This language can ask questions on the triple store that contains the graph data or the RDF data stored in it. So this is like a stack of technologies for semantic web. And if we want to compare that with tabular data, the data representation and the data model are the table. The data store are whatever software or place you put them, like Google Sheet or Microsoft Excel. The query language, there is no actually query language to ask a question directly on the CSV or the tabular data, but you need to use the software. For example, in Excel, you can use a filter. You can specify which columns do you want to filter, what is the conditions, and if you want to select a row, we can, with the mouse, just click on that row and you will have it selected. So this is the logic of dealing with tabular data, but in the semantic web stack, we have these 3 pieces: the query language, the data model, the RDF, and the data store. Also, comparing the same stack to the relational databases, if you're familiar with that, we have entity relation diagrams or tables that are linked to each other with relations. We have the data store or the databases. Maybe you heard of Oracle, MySQL, SQL Server, PostgreSQL, and so on. And you have the query language called SQL. It's fine if you're not aware of that. I'm just showing here that, like anything else on the computer, there is a stack of technologies, there is a stack of file formats and encodings that we need to understand to be able to leverage this, the semantic web in our case. So this was all of that general talk, identifying some concepts and acronyms. I want to dive a bit or be more specific, give an example of a knowledge graph and start learning SparkQL writing queries to explore it. The example that I will be using for this tutorial is called Kimball. Who heard or who is familiar with Kimball? Okay, Good enough, more than half people here, I think. So Kimball, it's a database for chemical substances along with their bioactivities. So it's initiative, or it's a project by the European Bioinformatics Institute, EBI, and they manually curate the literature, the publications, and they deposit in that database information about the chemical substances, the assays measuring their function against a protein, or their toxicity against a cell line, and so on. So it's life sciences data, chemical and biological, deposited in a database. Since this tutorial is related to life sciences, I chose this source of data. The thing about Kimball is EBI produces two versions of this resource. One of them is relational database in SQL format, and the other one is RDF data. So they provide the entire Kimball database in RDF format as a set of triples encoding all this information. But the thing is, they make it available for download as RDF files, but they do not provide the data. Let's get back here. They do not provide the triple store. So they do not load the data in a triple store where they host themselves and you can access it and query it. They've done that before in the past, but they stopped doing it at some point. And then the Department of Bioinformatics at Maastricht University, where I'm working in, decided to host that RDF, to load that RDF in a database or triple store, and to make it accessible to the scientific community to query with the SparkQL query language. So we will be diving a bit more into this resource. So this resource is already available on this URL, kimballmirror.rdf.bigcat-bioinformatics.org. I will give you a bit to just open that link. What you will see when you access this URL is this interface. And this interface is like an application. It's a query interface, allows you to write queries against that triple store, against that database that's storing our RDF data, our graph. This piece of software called Snorkel. So it's a SparkQL Explorer, and previously the Snorkel was an old SparkQL Explorer developed by DBpedia, and then we later modernized it, and we added features to it at the department at BCAT in Maastricht University. So, for example, we have now SparkQL Editor, where it highlights your SparkQL queries. This is the editor part where you write your query, and on the right side, this was very helpful feature we added to Snorkel, which allows you to specify a GitHub repository where you put all those query files in there, and you can just load the queries from any GitHub of choice, and you can reuse them. So you may want to ask many queries against a specific resource like Kimball, and you want to keep those queries saved somewhere. With this feature, you can organize your queries in folders in a GitHub repository, and just pasting the URL of that GitHub repository, and you will get them. You will get those queries available to use in the Kimball query interface. And you have also several buttons that allows you to download the results of your queries as in CSV, JSON, or XML, and you can also share those queries and get a short link for them. So also you can share the query with others. Okay, let's see. Yes. So this is the main interface of the query interface for the Kimball RDF. Here we have already made a GitHub repository with some of the queries that could be interesting. We will see some of them in this tutorial, and all what you need to do is to click on the query, and you will see it immediately populated. So when you click on this link, this file on GitHub will be fetched, and the content of it will be pasted here. So this way you don't need to retype your queries or memorize them or put them in a text file on your computer. You can just retrieve them and reuse them. And you can change this URL to any GitHub repository you use to load this, to get your queries from. I will come back to that in a bit. So this is the technical stuff part. This is our entrance, our gate to explore the Kimball knowledge graph. But before doing that, we want to talk a little bit about the model of the Kimball knowledge graph. So in the most simple example here, we've seen that our model is composed of two types of entities: person, right, and art. And we have from person three instances: Bob, Alice, and Leonardo da Vinci, and we have one instance of the art, right? And we have here, I think here, this is either a museum or this is a place or a video here. Maybe this is a media about the Mona Lisa. So we have three types of entities: a media, an art, a person, and we have three instances from the person, one instance from the art, and one instance from the media. Is that clear here? So this is the model. It's a simple model, three entities and instances of them, and they are linked together with predicates. In Kimball, we need to understand the model to be able to ask questions about it, right? So in Kimball, this is the model. It's bigger than this, but I only chose this chunk of it to explain it. It's better for explanation, and it's better for writing queries here. So the most basic or the most central piece is the assay. Who knows what is the assay is in biology or chemistry? Who worked with any scientific life sciences data? Okay, so an assay is like an experiment you design that composed of samples, and it's targeted to understand some phenomena like function of protein, interaction between a chemical and the protein, binding, for example, a toxicity of a material against the cell line, right? It's an experiment. And because of that, so the experiment, the assay, composed of multiple things. You have a substance. The substance could be a protein, could be a chemical compound, small molecule, or whatever. And you have a target. So you want to test something against something, right? It could be testing molecule or chemical against the protein or against the cell line, as we have here. So the assay is linked to a target, it's linked to substance, is linked to a cell line, and there is the activity. So the link between those two entities, they should be expressed, measured in a way, right, in the lab with a certain piece of equipment that telling us that this material with this concentration, if applied on this cell line, will be toxic, or it will report 50% cell deaths, 50% of the cell died, or 80%, or so on. So those are the main component, except the document and the source. Leave those out for a bit. So we have assay, we have substance, we have target, cell line, and the activity. The activity is the main output of the assay, right? And remember before when I talked about the metadata, that is implicit knowledge in the traditional tabular format, here we encode this metadata into two pieces, the source and the document. The document here is the place where you got this information about the assay. If it's a publication in the literature, then the document here is a journal article. It has a journal, it has an issue number, it has page start, page end, the year of publication, the authors, everything about the origin where this data was reported, right? So this information is explicitly encoded in this knowledge graph. And it's linked, so I can ask a question, give me all the materials that were tested in this document or in this journal article, right? We can ask this kind of questions. Give me all the assays or all the targets or all the activities that were mentioned in this document. So this is the metadata about our experimental about experimental data linked in one model, because everything is a triple. It doesn't matter if it's a document or an essay. Everything we can represent it as a triple, and they will be linked together. I will show a bit more complex image. Source is a Campbell. They provide, so every the document can have multiple types. The source, I will come to this later, but that's fine. Those essays, Campbell categorized them as scientific literature. So some of them can be sourced from scientific literature. Some of them can be, you will see here. Yeah. So the source has only one predicate or one set of the triples. The predicate is the label, and the value is literal, and it's literature, it's patent. Some of the data are coming from pharma companies, so we'll see the source is GlaxoSmith, or the source is AstraZeneca, or the source is Novartis, or so on. So the sources of the data is the institution or the third party where this data was coming from. Okay, so it could be extracted from patents or from the literature or from a company and so on. So they label all the essays with a source from a specific set of values. While here in the document is only a book, a dataset, publication, or patent. But they can, by adding this link, they can tell all these essays are coming from this pharma company, even if it's coming from a book or a dataset or publication related to that pharma company, right? So in this image, in the previous one, I only showed the main entities. So it's like the person and the art in the first graph. But we have more information linked to those entities, and this is where we show here. So for the document, for example, we have 4 set of triples linked to it. It's the document type and the value of it. So this triple document, subject, predicate, object. The object here is a literal, and the literal is a string and takes one of 4 values: book, dataset, publication, patent. Then we have another triple. It's document, the date of that document, and then the value is integer. Campbell only stores the year of that document, right? Usually in a journal you get the full date, but Campbell starts only the year, so the value is integer. While if it was a full date, integer doesn't work here. We should use XSD date. The title of that document, it's another triple, so document, title, and then literal, and they have the DOI, right? The DOI is another predicate, and they provide here URL. Similarly, the substance, there are more predicates linked to those entities, but I'm only mentioning the basic ones that are needed to fulfill the content of this tutorial. The substance, there is a triple called substance type, telling us what is the information encoded, what is the type of this substance used in this essay, which is reported in this document, and then set of attributes. This is a predicate, identifier of predicate called has attribute, and you link it. So if I go back to the first, this one, those attributes would be the core size, the hydrodynamic size, the surface charge, the surface area of the material. So the material is the substance in this case, and those properties are each one of those. Okay, let me get back. So here the substance, every substance can have multiple set of triples, each one of them pointing to a different property, right? And this property, each property has different value. So if we want to apply that on the first data set of the Excel sheet, it will be here aluminum oxide, AlO3 is the substance, and then it has attribute, 1 triple for the core size, 1 triple for the surface charge, 1 triple for the surface area, and so on. And every one of those has values. the essay, as we said, the essay has links to all of those. So the essay belongs to a source, it's belong to a document, it reports activities, it has target and cell line, and it also has essay type. And there are 5 types of essays in Campbell: functional, binding, ADME, toxicity, physiochemical, and unassigned. So if you're familiar with the lab experiments, any one of those essays are reported in Campbell. Yes? Yeah.
So every sort of attribute of one of those nodes has a name. But for chemical substance, it's just really name value.
Name value pairs?
Yeah, so you have a substance.
Yes.
Has an attribute, which is some property.
Yes.
Which has a value. Why not just do a predicate for each of the properties?
So this is a triple: subject, substance, predicate has attribute, and object, the property. And the object here is a resource in itself. And there is another triple. Yeah, subject is the property, is the identifier, the URI, predicate, object, right? So they are 2 entities linked to each other.
Okay. And what is the property you said was, what's an example of this property?
An example of the property could be the molecular weight, could be the size, could be this charge.
So why would you have substance has molecular weight and just a molecular weight?
Because with has attributes, it's one predicate that can point to different types of properties. The way the model is a design choice by whatever party is making it, right? So here they decided, I'm gonna make one a predicate called has attribute, and then link it to different types of attribute, whatever they are. Your design proposition could be have a predicate called has molecular size that only links to property IRIs of the type molecular weight, right? And then have another predicate called has charge, only links to a node of type charge, right? Yeah. So you can do that.
But it seems if you go the name value pair, now you're, instead of staying within the model, you're going kind of meta.
Going what?
You're going at the level of the meta model. So in other words, you have a model.
There is a level of abstraction here, but yes, indeed.
Yeah.
So in your queries, now you need, if you ask the question, give me all the properties linking to a substance, it will give you properties of different types. Now you need to add one extra constraint in your query. Tell me all the properties, and in the second level, filter only the properties that are of molecular weight. Exactly. The design of the model, it's up to the people who are making this model. And similar, there is this famous saying, all models are wrong, but some are useful, right? So, and this not only applies in machine learning or mechanistic modeling, it is also in data modeling, right? So all the models has a certain level of abstraction. There are some details that are, you decide to go either too deep into the definitions of the entities and the predicates, or to be a bit abstract. And so in my PhD, we're working about data modeling for nanomaterials, for nano safety experiments. And the size, for example, always is a huge debate. Nanomaterials can have different shapes. So if the nanomaterial is spherical, the size is reported as a diameter, right? So if it's cylindrical, the size is 2 values, the length and the diameter. If it's engineered nanomaterials with multiple sizes, the size is either a range, minimum this diameter to maximum, or it's a mean plus minus standard deviation. So it's a size of this mean around that. So whenever you mention to experimental nanotoxicology or nanomaterial person, and you say size, you say this is meaningless to me, right? It's too abstract. You need to tell me exactly, is this size, is it diameter, or it's length and width, or something else. So this level of abstraction and details is really depending on who are you working with, how much detail you want to capture in your model, right? And there is no right and wrong. It's why are you creating this model? What kind of questions you want to ask, retrieve from it? All of those determine how do you model the data, right?
design choices.
Yeah.
And several places in this model, it looks like there's a controlled vocabulary managed as literal.
So in the model, it doesn't specify the literal values, but Kimball, they control that themselves. Yeah. So in RDF, it's if you said it's a string, there is no way to say there is specific strings. But if you only inputted,
They've chosen the strings that they're practicing.
Yeah.
So why not entities?
That's a good
For
question.
example, assay type what I might be interested in toxicity assays.
Yeah.
I would think if you wanted to reverse something, but that's not the choice that they made here.
Yeah, that's a great idea. The preferences of the linked data is always to use entities when possible and links to them. But here, I have no. Or maybe this is the level of detail they wanted to stop at. We're not interested in linking more things, adding more entities and branching from them. We only want to know this assay type if it's one of those 6 or, right? So that's why they are literals. But yeah, another design choice could be, they could be their own entities with URIs. Yeah. So here, yeah, sure.
Is this property IRI?
Yeah, since IRI, that means it's a resource and it has RDF type linked to it. So it is a molecular weight, so it is a member of class. Yeah, sure. All the ones that are in blue, those are URIs or IRIs. They have RDF type class linked to them.
Who's maintaining this model? Because assay is a choice, but I see a lot of non-existing themes there, or I can put my essays in this scheme. So
it's the ABI. The ABI is producing the RDF.
Force thoughts about.
That's a good question. And this is not only the model, but also the vocabulary where those things mentioned. So there is other vocabularies like the bioassay ontology where they call an assay bioassay, right? So we have this problem like in other disciplines. In the semantic web, every group says, okay, this ontology or this vocabulary or this model is lacking a couple of terms. We're going to make our own ontology. And they go for their own models. And then it go obsolete in a couple of years. The funding is gone, and then they make new. Yeah.
So I guess this is why they minimized the model and they had set another abstraction for the table system.
That could be.
But then the question to you, because they are not providing the triple store, you are providing it. How frequent is the update? Are you updating live
whenever they have a new version? Yeah. No, we keep an eye on them. Yeah. So yeah, we're not coordinating, like we're not officially ABI. Yeah. So when we see there is a new version out, we update it shortly after the release. Yeah. So here, since this tutorial is about constructing the knowledge graph and learning SparkQL, we're not going it's not up to me to decide what model a certain resource is using or why they designed it this way. But this is the model, and we're going to use it to learn how to write SparkQL queries to answer questions. Okay, so this is the first thing about SparkQL query. The query structure, the basic query structure. To select information, it has 3 keywords, or at least 2 keywords. It's the select keyword and the where. Okay, and there are a couple of things we need to pay attention to. In the where, the select, you specify which variables you want in the output table coming out from the knowledge graph, and in the where clause, you specify all the conditions or the filtering that you want to apply on the graph to get the data from. So the variables are, the name of the variable doesn't matter. You can choose whatever you want, and you just put a question mark before it. Once you put a question mark before any string is considered a variable, and every triple you want to filter the graph on, it should end with a dot. Those are the 2 things you need to know about the SparkQL query, the selected query for now, right? So you select, you say, I want to select this information back. I want to get them back from the graph. And in the where section, you define based on what I want to do this selection. Okay? So we will go through using the model, and we will go through explorations of this of the graph, and we will learn multiple things, multiple additions to the Spark QL query along the way. So for example, if we go to this, I'm gonna put here, there is a list of prefixes. Those are the shortcuts of the URIs used in the graph. I'm gonna copy paste them into the, you always need the prefixes to avoid rewriting them again and again. And the first thing is the select. I'm gonna leave this here, the where, open curly bracket, and this is the most basic query you can write. Here you need to specify which variable you need to select, and in the where clause you need to specify the conditions. So if I want to get, let me get back here. If I want to get, for example, a list of the URIs of essays, I want to get a list of the URIs of all the objects or instances of the class essay in a simple form. So I can call my variable essay, for example. Yes, yeah, that's good. Yeah, sure. So I define a variable called essay, and I want to use the predicate A or RDF type. It's the same. And then since the prefix of Campbell, this Campbell model is called Campbell or Campbell here, so I say Campbell essay and then a dot. What do you expect that will happen here? So the query engine, the Spark QL engine, where this RDF data is loaded, will start filtering the graph. So it will look for any entity, any instance that has a type essay. That means here it will look for any circles that are linked with the predicate to this class called essay, and it will return them back, right? So if I want to get the URLs of those essays, I just put the essay here, right? This query will give me all the URIs of the essays stored in Campbell, but I don't. I want to limit this a bit. So there is a keyword called limit, and then you specify how many records you want to bring back from the query. So this is a very basic query. If I hit the query button, you see the results. Those are the IRIs of 10 essays in Campbell. Okay? This is not informative, right? I have nothing from those IRIs because I'm getting the nodes, I'm getting the identifiers of those essays. There is not a lot of information there, but with this query, I got 10 essays from Campbell. If I go back to the model, I see that the essay has a type, right? It's linked to with the predicate essay type to literal. So I can extend my query a bit, and I can say, for each one of the essays you selected in line 13, give me Campbell essay type, right? It's called essay type, and then a variable, because this is whatever value it has, I will call it essay type 2. So here, the second part, it will select from all those essays only the ones that have a specific predicate called essay type linking to a value, whatever value it is. But if I hit the query button, I will still get only the URIs of the essays. Why? Because I didn't tell the select that I want to get the type also, the type variable back. If I get the type variable back and I hit the query again, I will get 10 different essays with their type. In this case, the first 10 that returned by the query, all of them are of the type functional. Okay? Is this hard or is it clear?
Then how does the KYC start? Where does the starting point from? Is it usually in some assignment or?
No, they are not ordered originally, and the implementation of how the query is executed is vendor dependent. So every triple store will have their own algorithm where to start from, right? So they keep indexes of all the URIs of the nodes and all the object values, and then they traverse it, or they handle the query in different ways. So now this query is not useful because we're getting the first 10 essays you can get.
You first come the on the spot that I tried it.
Yes, sure. No. What I can do is every query we have. What I can now get this. I can also copy the URL. Put it here. I think this will work if you open it. Okay, this is the old one.
Final moment.
I don't know why this button is not working here. I'm not sure now. But I can also copy the entire query to Slack. Okay. I will copy the queries into Slack to keep them for reference. So there is another, if I want to get more information about this essay, so there is another, it's not here in the, here it is. There is another property or a triple linked to the essay. It uses the predicate description, right, from the prefix DC terms, and it will return also literal. So this information, it will give us a description about this essay. So if I use here DC terms, description, and then essay disk, for example, and I get that back to the you see here, now it's getting more meaningful. I know that this node or this resource in Kimball, it represents an essay that has a type functional essay, and it has a full description. The descriptions in Kimball, so for example, the type of the essay, they do not have it in an independent predicate where you can access like this is MTT essay or cell viability essay or something. They put it in the description. So you can read this description and you know this is, for example, an activity in specific cells used with a drug, whatever, right? So this is more informative now because at least I know this resource, what is it about? What is the description of this essay? Okay? So now we're getting more and more information from this. We started from the essay, we accessed 2 of its attributes, and now we're getting 3 triples for each essay. So now we're getting a triple that is resource is a type of the class essay, and we get the type and we get the description, and we only return those variables. So we're getting a table from this subset of the graph. Okay? So the single triple pattern is when you only mention single triple in your where clause, and the multiple triple patterns and when you mention multiple patterns like I did here. So it becomes like a join between these three sets. So the first thing, it will get all the resources that are a type of essay, and then it will filter them further to select only the ones that have a type, whatever that type is, and then it will get the ones that have a description, and so on. So, and I'm using variables for everything here, right? So that means give me any node, any resource in the graph that is linked to any other resource in the graph through this predicate called essay type. But in the SparkQL query, I can be more specific. It's already 10:30, right? Yeah. More specific. Let me get back. So here, if I want to get the essays that are of a specific type, like toxicity ones, right? I don't want to get any essay type. I want only to get the toxicity ones. I can replace this with toxicity, right? If I do the query, now we removed the essay type as a variable because we replaced it with hard-coded type of the essay, and I do the query again, I will get only the essays of type toxicity. You see now how can I filter this graph more and more? Of course, description is there is no standard values, there is no specific values. The description is depending on each one, so it's not very helpful if I want to search for, unless I know exactly what that description is. It doesn't make sense to filter on specific description unless I already know it and I want to look it up specifically.
Can you choose from list instead of typing in the toxicity?
That's the thing. Since the model of Kimball provides this object here, the object of the essay type as literal, so we have list of strings and it's not a list. You mean a drop down or something? In this, yeah, the SparkQL is a query language. You not read to write everything explicitly, but there are ways where you can develop an interface on top of this, where you can get the input from a drop down and then substitute it in the query. But the query language is the most abstract way of interacting with the database. So you need to be here everything mentioned explicitly. So if I want to extend this query a bit, and we know from the model that the essay is linked to a document with has document, okay? I want to get for each one of those essays, what is the document or the publication where they are mentioned in the first place. So I say essay, it's Kimball has document, so it's Kimball document, and then document, and I know from the model that the document has a title, so I can immediately get the title. I'm not interested in getting, so this time I start with the document, right? Because this triple is now document, title, literal. So in the next part, whatever document you got linked to those essays, I want TC terms, title, and I can call it document title, for example. And here I say document title. And we make the query, and we get whatever document title linked. This is the origin where this essay was extracted from. Okay? So if I want to be more specific and search for document types of only a publication, I can put further filter here. Okay, and say document, Kimball, document type, and then doc type. Sorry, here I want publication. And you see here, it will give the only the documents of type publication. If I want to get the DOI of that publication, I say document DOI and then DOI, and I add it to the list of select. And you will see I will get the DOI of the publication where those essays were reported in the first place. Here I want to get, for example, for a specific molecule, which is acetaminophen. This is the chemical compound of paracetamol. I want to see all the assays that measure the potency of acetaminophen against a specific target. So here I have the substance here. I need to fix the name of that substance, right? Acetaminophen, and I need the activity, and I need the assay. I need 3 pieces of information, and I need the target. So 4 pieces of information, right? So first thing here, I got all the assays that has a target, whatever it is. So I got this triple assay has target, and then I got an activity that links both to the assay, to an assay and the molecule. So this is the activity, and the activity has assay, and the activity has molecule. And then I obtained the label of the target. So every entity in Kimball has the predicate RDFS label, so you can get the label of that target. But for the molecule, I'm specifying the label explicitly to be acetaminophen. So I want only to filter the molecules that are acetaminophen. And for the assays, as we did before, I wanted the description of the assay. So I got the activity that links to an assay. I got the description of the assay. And I also got the molecules that links to the activity. The molecule, I specified the label of it to be acetaminophen, and the activity has a type, and the type I specified it as the potency, for example, and I obtained the value and the unit of that activity. If you hit the query, you will see the results. We have the target, which is a protein. We have the description of the assay. We have the value of the potency and the unit, for example. So if you want to ask questions, which assays studied this compound against which target and what was the potency of it, with this query you can get this level of details. So again, I started with the assay here. I got link to the target, and from the activity, I link to that assay, and I link to the substance, and I specified the type to be a potency, and then I got the value and the unit. The unit is not here in the graph, but it's the predicate units along with the unit as a variable. And then in the select, I wanted the target label, the assay label, the value, and the unit. And with the query, you can get this information. So this is another query with the same, so nothing new in the SPARQL query in terms of keywords or other features, but we are traversing the graph in different ways. We are specifying specific things. So the thing here is, as the question here before, how do we know, is there a way of having a drop down or something to select features? And the thing in SPARQL, you don't have these graphical features. One way that you can get help is to go to Kimball, for example, the actual Kimball website. You can go to Browse Kimball, and you can search here to, if you need a specific compound, for example, if I said acetaminophen, as a compound. It will give me the entry of acetaminophen. From there, I can get either the identifier or the name, and I can use it back in the query. Right, so you can get the information about the chemicals from the search in Kimball if you're looking for specific information, and then you can get all the remaining stuff like the potency, for example, potency assays and their values from there. But yeah, you need to explore this through the database in order to get this information or to get the specific name of that. So on the SPARQL, it's very low level. You need to know all these values in order to reach that part of the graph that you want. Otherwise, you can replace this with a variable name like this, molecular label, but you will get this information for all the labels for all the molecules in Kimball, and yeah, it depends on what you want to do. If you want to go through them, some of the molecules labels are just identifiers. Some of them has the full name of the molecule, so it could be messy a bit. But with the search on the Kimball website, you can narrow down these results to the specific compound candidate you want to look at. So another keyword in SPARQL query that could be handy is called bind. So when you introduce those triple patterns, you only get what's inside Kimball, but sometimes you wanna manipulate these results before adding them to the select section. So for example, here the value and the units are 2 columns. I'm getting them in 2 variables and putting them into columns. What if I want to produce more natural text out of this and put them in a single column? How would I do that? The word bind in SPARQL allows you to perform functions on one or more variables in the where part and assign a variable to this processing. So there is a function called, for example, concat. This is concatenation of text, where I can, for example, mix 2 variables from the where clause and put this output in the select. So the example here, I want to produce one column called value, and I want it to contain both the numerical value and the units in one column, and without having them in this view. So I can do here. There is a function called string also to convert everything to string. So value, let me show you. Space unit. The bind, it needs to assign whatever result of the function to a variable name. So using the keyword as, and let's say value unit. So here in this line, we take the value and the unit variables that we obtained through the graph traversal here. We concatenated them using the concat function. The concat function takes as many parameters as you want. So maybe you want to create a text out of it, right? You want to combine several fields, so you can add commas and text as much as you want. And here I only added 3 pieces, the value, then a space, then the unit. And I assign the result of the concatenation with the keyword as to a new variable called value unit. Now I should put the value unit in the select. I will leave the separated ones just for comparison. When you run the query, this one is more. Yeah. So you can see now I have a new variable called value unit where the unit is concatenated along with the text. Well, maybe here the added value is not much, but you may need to do that and combine stuff. And then for concat is not the only function. You may want to add numbers to each other. You want to, for example, calculate a percentage from a number, right? Sometimes you have value as a percentage between 0 and 1, and you want to make it as a percentage. You multiply by 100 and you add the percentage sign. So you manipulate the variables of your of the patterns, and you return that as a variable to the select. There is another case. Let me see the DOI example. Let me use that again. So in this example, we obtained 10 random essays with their description, the document title where they obtained from, and the DOI. But Kimball stores the DOI as a string, so only the identifier part with the DOI and not the full URL. So in order to do that, you have to copy this, go to Google, paste it, and to find the right URL. We can use the bind word here. We do bind, concat, make sure the DOI is a string. So if I want to construct a full URL from the DOI string, I need to add in the first of it to the beginning of it https doi.org. So with this part now, I'm using concat to concatenate the first part of the URL to the unique string that Kimball is providing, and assigning that to a new variable called DOI URL. I'm going to replace the old one with this one. When you do query, there is another function. So the result of the concat is a string. Concat returned a literal, but I want it to be a clickable string, and the function for that is called IRI. IRI is convert whatever the string inside of the concat, returning from the concat function, to a valid IRI. In this case, it's a URL because we constructed it to be this case, in this way. So if we run the query, now we see we have a link. If you go and you open in a new page, and you will reach the publication page. So this is another helpful use of the bind query. So we constructed the full URL of the publications from the DOI identifier stored in Kimball, and we can now this is helpful for provenance, because now there is an essay claiming that they did in vivo toxic effect in mouse in specific conditions, and we want to know where it is coming from. Now we have a link to the actual publication using that SparkQL query. We can dive even more in detail. So every document is linked to a journal. We can get all the journals, for example, that studied this substance. We can group them by the number of publications per year or per substance, and there is no limit to what you can do here. But this is just an example of constructing the URL. Okay. I will copy the stack. I will show another example for bind. We will use the previous. So this is the previous example for acetaminophen. And if I want to create a clickable link for the actual page of acetaminophen on Kimball from the Kimball ID here, so there is a predicate linked to the molecule called Kimball ID. So by doing this, I'm already obtaining the identifier of this molecule, which is acetaminophen in Kimball. But this is, if I run, let me put it in the select and run the page and run the query. You see here, it's the same identifier, of course, because I limited the compounds to acetaminophen, but it is just a text. If I want to get a clickable link to the page of it, first let me see how any page looks like. So this is the structure of the URL to the Kimball website. You need to have this part and then the identifier, right? So now I can do in my query bind, and then I want an IRI, and then concat the first part of the query, and then a string, and then I should get the molecule ID. Close the first one, close the concat IRI as, let's say, molecule URL. Okay, and now instead of the ID here, I'm gonna make the molecule URL. If I run the query, now I have a full URL. If I open it, I should get the acetaminophen page on Kimball. And you can see here. So from the identifier in the RDF using the bind function, we reconstruct the URL on the actual Kimball, and we obtain the links, the same as we did with the GUI. So these are some of the how can the bind function can be helpful. It's to manipulate the results, manipulate the fields in the graph, and assign them to a new variable and report that back to the select part of the query.
I don't know, it's possible to use prefix in your concat.
But concat only takes strings, so either the variable or the full string. But no, it's not able to use it the prefix there. Because if you already have a full IRI, it will be already in the variable, or it will be already here. You don't need to use the prefix there. But here we're constructing something external to the graph. This is a URL not in the graph itself. So there is another keyword in SparkQL called filter. There's also many use cases for the filter function, but here I will show an example of it. So you can filter any variable in your SparkQL query with all the types of equal, bigger than, smaller than, not equal, and so on. So if you want to filter, give me all the publications published after a certain year, you can do filter and then year, and here bigger than, for example, and you put 2021 or whatever number. In this case, in this query, I used it to filter all the I want to see is for a specific drug called vorinostat. This is used to treat some sort of cancer, and I want to see all the assays that tested this drug against any one of the histone deacetylase proteins. There are 7 histone deacetylase proteins, and I want to get all the assays that studied the vorinostat drug against those the family of proteins. And to do that, I filtered on the target label that starts with, so there is a function called str start. So that means if the target label starts with histone deacetylase, whatever comes after it, that's included. And then you will get, for example, 4, 7, 3, all of them here. And the count here, I wanted in this query to count how many publications already reported assays studying the vorinostat against one of the histone deacetylase. So this is also use case of the filter function or the filter keyword in the SparkQL query.
Sorry, what? Is there overlap in functionality between filter and the where?
You mean with the direct replacement? So here, if I did filter type equals single protein, I could also do directly copy this and replace it here, right? But filter inside of it can be any type of comparison, or it could be a function. For exact match, like equality here, it's exactly the same of putting it in the triple. But if you have bigger than, smaller than, then you cannot substitute it. Yeah, or a function like a string starts with, then it doesn't work anymore. But for exact match, yeah, it's exactly the same if you replaced it instead of the variable. So I would like to move now. Now you've seen how this part of SparkQL, the possibilities here. It's select and where clause, and inside of it you can traverse through the graph. You can select specific triples. You can get the variables. You can manipulate them and report whatever you want. There is another type of SparkQL queries that they are called the construct queries. So instead of the construct, we have instead of the select, we have the keyword construct. And this is how it looks like. So instead of select and then a list of variables, you do construct and the where clause. But here, the construct query returns the triples themselves. So you do not return a table, but all the triples you select in the where clause, you can return them into you actually get a graph as an output of it. So let me give an example. So in this query, I'm selecting all the URIs, all the entities that has a target, whatever that target is, right? That means I will get a set of triples of URI, predicate has target, URI. In the construct, if I did the same, the output will be an RDF file containing a set of triples. It's not a table, it's the exact triples of RDF returning back to me. And this will be helpful for the next part where we'll talk about knowledge graph construction. Why I said it doesn't require any programming language, because here the transformation is built specifically using the construct query. We're not using a programming language that getting the data as a table and then doing something with the table and creating RDF from it again. But it's actually create RDF from the RDF. It takes a subset of the data, it could manipulate it in a way, and the result will be an actual graph. What we can do with the construct query is not to only get the data as is, but we can change it. So for example, if I have, in this simple graph, I have a URI that links to the target URI with a predicate called has target. But what if I have another ontology, maybe the bioassay ontology, and it has a predicate called has target like this? If I am integrating or I want to enrich my current graph with more data from Kimball, I want also to change the relations. I want to harmonize them in another way. So with this example, I'm getting the triples from Kimball, but I am changing the predicates into a different model. So I am reshaping the graph itself, and I'm getting entirely different set of triples as output because I'm using a different predicate here. And that's what are we gonna do in the knowledge graph construction part. So in summary, what happened with this command when you put docker compose up D is three things. First, the link pipes software, which is a web-based browser that you have now on your browser, to create knowledge graph construction pipelines or RDF construction pipelines. This was installed, downloaded to your computer, started the server up, and you can access it from the browser. The second piece of software that already happened, downloaded and started with the Docker Compose is a triple store. Virtuoso triple store. This is the database I told you that you need to load the RDF files into to be able to query them. This is also started and it's ready for the RDF to be loaded into them. The third piece of store is the Snorkel interface, the query interface that we are doing now, writing the queries in. This one, but not the one on Kimball, but local Snorkel on your computer. So on Slack, if you want to visit the Snorkel interface, go to localhost, but 8080, the port, is to open it in a new tab so you can have them next to each other. Typical acronym in data science or data engineering, where you always have, you need pipelines that extract data from somewhere, do some modifications or calculations or transformations, and load it in a target database. So this is where the name ETL coming from. And this platform is specific to RDF data or semantic web data. So this is very convenient to use for knowledge graphs. I will open the website for it. So linked pipes ETL, if you open it, as you've seen, if you open the page already, you have an empty. In your case, I have here 3 elements. In your case, you will have 0. It's empty, right? So we have at the top 2 important things: the pipelines and the executions. The pipeline is any step, it's a series of steps that you perform in order to get the data from somewhere, transform it, and put it somewhere else. It doesn't matter what you're gonna do with it or what kind of data, but it's a series of steps called a pipeline. The executions are a history of every time you run that pipeline, right? If you run this pipeline today on an external data source and that data source changed tomorrow, so this execution of today will be different from the execution of tomorrow. That's why they keep track of not only the pipeline, the definition of it, but also for every time you run that pipeline, what is the output from it. So in order to make a new pipeline, if you just hover over this button below and you click on the plus sign, you will have an empty. So this is the design interface where you're gonna create the pipeline. And I'm going back to this slide. So in any ETL platform, whatever it is, for semantic web or not, we have this concept: extract, transform, and load. And we have different, those are called, call them whatever you want, nodes or functions. So the pipeline is in itself is like a graph, right? The pipeline is a series of steps connected to each other. So I will call those nodes. We have 3 types of nodes in linked pipes ETL. The extract nodes, they are colored like, I don't know, orange. And the transform loads are blue, and the load nodes are green. The extract loads are already pieces of software or of a script that performs the function of getting the data from somewhere. Okay? So here we have an example of a node called HTTP GET. HTTP GET, that means you will be able to give a URL to this node, and it will download the file, a URL of a file. It will download that file to the place where your pipeline is. So this is one way of extracting data, getting a file from the internet. Another one of them, for example, SparkQL endpoint select. This one will query an external SparkQL endpoint like Kimball, for example, and it will get the data back from it, either as a graph or as a table. So those are ways of extracting data from somewhere. Okay? If we go here, click anywhere you want, any empty place, and the left icon, it says insert component. If you click on the insert component, you will see all this list of components. The ones that have arrow to the bottom, toward bottom, those are extract nodes. And we want to start, any pipeline should start with getting the data from somewhere, right? You have, for example, files from local. If you have files on your local computer and you want to import them. Extract from FTP. If you have remote server where you are producing the files of your experiments or whatever, and you want to get the data. HTTP GET, if the file already accessible online, like a GitHub repository, for example. And this is what we're going to use in this example today. So HTTP GET, once you click on it, you will see the node already in the designer interface, right? The pencil icon, it says edit. If you click on it, you will see configuration, the file URL, the file name, and some tick boxes. The file URL is in our case, our pipeline should download the dataset, CSV dataset, the thing I've spoke in the beginning. We want to go from this tabular format into RDF. So here we're going to give the URL of CSV dataset, the file name, whatever the file you want to name it on your computer, and that's it. If you want to do that yourself and you are a Python programmer or Java programmer, you need to import the relevant package. You need to send the request to get the file. You need to be able to download the file, to parse it. You need to know the packages that handle CSV or TSV or whatever, right? So this is what I meant from the title of the presentation, with more semantics and less code. One command in your terminal, Docker compose up. You have everything. You have the triple store, the query interface, and the pipeline building. And now we're gonna build our pipeline node by node, and every node will encapsulate certain functionality that will help us toward getting to the knowledge graph. So if we went to the GitHub repository URL, I have a folder called data, and inside of it there is data.csv. If we check this document, it's similar to the one I had in the first slides. This is a toxicity assay experimental data for nanomaterials, where we have each line represent an assay sample. We have the material, we have several properties related to it, like the core size or the charge or whatever. We have the assay, we have the cell line, species, time and dose, the viability, the actual toxicity, and the assessment, if it's toxic or not toxic. This is the data set that we want to convert into a knowledge graph, and we're going to follow. So as we said before, if you want to go into knowledge graph, you need to follow a semantic model, right? And since we learned SparkQL on the Campbell semantic model, we're going to convert this data into a knowledge graph following, again, the Campbell semantic model. Okay? In the first part in SparkQL, we already have the data in RDF following the semantic model, and we're trying to write queries to extract data, to extract information. We were running arbitrary queries to get potency, for example, or publications or essays. Now we're going to do the other way around. We're going to convert this data into Campbell, following the Campbell semantic model as RDF, and then we can make it available for others to query, or we can write our own queries onto it. Okay? So this file is already online. Yeah, sorry.
Can I ask, how did you
How did you what?
template so the tabular data?
That's what we're gonna do in the pipeline. That's what we're gonna do. So the first step is to get the data into the pipeline, right? So this data is already available online. We provide it. So we want the URL of this file. If you go to the open the CSV, I will go back, and you can click on the row. This will give you the full URL of this data. So copy that, and we go back to the linked pipes page, and we paste that URL. So here we have the full URL of the CSV data. It could be some file on your institution. It could be publication, supplementary materials publication, anything available online, accessible online. You can just copy the URL of that CSV and put it here. The file name is like the name that you want to save on your pipeline or on your computer. So let's call it data.csv. Okay. We do save changes. Everyone is following? Yeah. You can also in the general tab name that step. So now it's called HTTP get. I can call it, for example, get file from GitHub repo. This is to make your pipeline more understandable. There is a function, there is a button at the bottom called debug to this component. That means run all the steps until this component. This is the first step. So if we click on it, it will only run this step. Once you click on run function, the tab on the top will switch from the pipelines to the executions, because now we're executing the pipeline. Okay, so you see the color changes. The orange means that now we are in the execution part. So a copy of that pipeline is invoked, is being running. All the steps are being executed, and then you will see that version of the execution, that execution, specific execution. So now we have only one step, and that step downloaded the data from the internet. The nice thing here, every node in linked pipes have inputs and outputs, right? In the execution, if you click on the output, the connection, it will show you exactly what is the output of that step. And now we see there is a file called data.csv. This is already on our computer. That means that node already went to GitHub, got that CSV file, renamed it to data.csv, and we have it locally now. If you click on it, you will see you can validate that the download happened correctly. It's inside the Docker image, so you don't have physical access directly to it. But this is not what we want here. What we want actually is the data to be in RDF and already loaded in the triple store, where we can just open localhost 8088 and start running queries against it. Right? So this is the ultimate aim, is we convert the data not only to physical file, but to RDF on a live SparkQL endpoint where people can query or you can query. So this is how the aim.
Instead of getting the data from file, could you omit the database or you?
So everything, all the capabilities of this platform is available in those points. If there is a one that is connect, so you have extract from FTP, HTTP, pipeline input, SparkQL endpoint. So for the SparkQL ones, you can connect to any SparkQL endpoint and get the data as much on live SparkQL endpoint with a select or construct. But I don't see one that connects for SQL, for example, right? Since this is targeted to semantic web, it's all these functions are tailored for that. But there are many ETL designers that are connect with Oracle, MySQL, or even cloud services and so on. So everyone is here now. So now we have our data, and we want to add a new step. So now the extract is done. We have the file, the CSV file on our machine. We want to go into a transformation now of this data. There is a very handy node. This is the symbol of transformation. All the ones that have this intersecting arrows, that means it's a transformation node. There is a node called tabular. And this does a lot of work already. So the tabular one, let me go back to this. when I was talking at the beginning about how would you, for example, think of this CSV as in terms of triples, right? So the CSV is composed of rows, columns, and cells. If you want, in the most naive way, convert this data into RDF without any semantic meaning, without following any semantic model, we can say every row is an IRI. So we give an identifier to the row, right? The column name is the predicate, and the cell value is the object. This is very naive, but it is RDF, right? So in this case, we will have full IRI ending with 1 for row num1, and then we will have a predicate called material, and then the object will be AL203. Then we will have another triple for the same row number, predicate core size, and then the value 39.7. You get the point? That's what the tabular step does. It takes that CSV file and it creates an entire RDF graph for triples of all this row, predicate from the column, and the cell as a value. If we click on the edit part, it will give us a lot of configurations. So the input file, CSV is not standardized all the time that comma is a separator. If you're working with Excel, the modern Excels use a semicolon as a separator, for example. So here you can specify the delimiter. This is what is the value that's separating your columns. If you have strings that contains that delimiter, you don't want to escape it. So this is the quote character, the encoding of the file. It asks you, does the table have header row? So do you want to consider the first line as the header? It's already checked by default, which makes sense because CSV, even without a header, it's even worse than one with a header, right? Because you don't know what are these values are. And then trim white spaces for cells. I think this is a handy option to tick, because sometimes if you have a cell line called, MTC space, it's different than MTC, right? Both of them are strings, so you want to trim the white spaces from both ends of the cells. Then you have, now we need to construct the IRI. This is what I told you about before. The IRI, if you're working with the web, with linked, it's better to be real URL where you can visit, but here we're working with our data on our computer, so we need to construct an IRI. It doesn't have to be a real thing. So the default resource IRI template. This is the template that it will be the subject for all the generated data, right? We can come up with whatever you want. I will say HTTP : SWOT for HCLS /tutorial /row, okay? And then here we need to put between curly brackets what is the name of the column in the CSV that will be substituted to generate the IRIs for the rows. It was called row num, right? Yeah. So what happens now is for every line in that CSV, it will create a subject called SWOT for SLS tutorial row 1, 2, 3, 4, 5. And then it will link it to the columns and cells for every row. It will generate triples from each one of those. Okay? There are more options below. Rows skipped after headers. Right? Sometimes you have a header and then you have a bunch of comments with the hashtags. I've seen that in data like Uniprot or stuff. So here there are configurations of how do you, so trying to, all of these things you need to, if you are a programmer, you need to write code to deal with these situations. Here they make it in a graphical user interface where you customize a node toward your input file. So for this one, there is nothing else we need to be checked. Save changes. Now we need to link the output of the first step to be input for the next one. So now the first one is the extract. We downloaded the data. We just click on the output of it. and we link it as input for the tabular. That's all what we need to do. Now, the same button, debug to this component. You see all of them are green. Now we are in execution, so we can see the output of each step. So I will repeat this one. I'm checking, it's the same data, that's good. The tabular one, if we click on it, okay. You see, now we have data.ttl. TTL is the RDF format, it's called turtle format. Let's open it and let's see. So the first line is the subject. It is full IRI for the row, for the first row of the Excel file or the CSV file, right? It took the identifier, the ID, the row number from it, and it will make it as a full valid IRI. Then, for each one of the columns, you see row num, material, core size, hydro size, surface charge, specific surface charge. It created the predicates from each one of the columns. Those are the predicates, and the values of the cells are objects. So in turtle format, instead of the dot, if you want to create multiple predicate object pairs for the same source, for the same subject, you can put semicolon instead of the dot and just put the predicate objects until you finish, you end with a dot. You can do that also in SparkQL, but for clarity, I was repeating the essay and the compound every time. So now it's a single subject with predicate object pairs linked to it. And it is RDF, it is semantic data representing every row, but it is copying the mentality of the CSV, right? Because now we have a row is represented by a subject, every column is a predicate, and the values, and you see the values, all of them are strings. It's single quotes because it's never understandable, or it's never inferable from the CSV if this is a number or not. And this is what we want to enhance in the transformation. Next transformation step, we want to go from this model, this CSV based model, into the Kimball model. Okay? Yeah.
And NT cells will also create.
Well, I'm not sure if there was I think a choice before about it. I'm not totally sure. I need to check. But anyway, even if it does, we can in the next step we can filter those out. Okay, so you can see. Yeah, sorry.
Yep. So in order to use this data model, you have to create a template that defines all these two bits, right? Like a.
Yeah, linked pipes ETL took care of that for us. The template is that the column name is the predicate, and they put the prefix is a file and then the name of the file that you saved in the first place. So it's always unique to your file name. And then the object is the value in that cell, and the subject, you constructed that IRI with a template, right? But
so the template are by default imported from this program, right? So then I change the template. So rather than use this this data model, can I use it for a different data model that is not done? But
the tabular node, that's the job of the tabular node, is to create tables into this model. The only thing you change is how do you parse the CSV file, what is the delimiter, and what is the IRI template. But you cannot change how the triples. Yeah, you cannot change the triples. But yeah, sorry.
I was gonna say I ran it, but I'm getting an empty file. I'm not getting turtle, just a 0 kilobyte file bubbles. So something looks suppose wrong.
Okay, you have this. You have the same, exactly the same.
I get an error on the W.
Error? What does it say? Did you link them?
It's in one edge with the pipeline. I get it right.
Yeah. Around tabular.
And it says that there's something wrong with
Okay, then let's go back here. Then check. You have to put the row number between curly brackets, and you have a backslash, you have a forward slash before.
I'm sorry, what about stuff? Right, it had risk of independence of the Hanoi.
Well, theoretically, it shouldn't make any difference. Can check.
The depth like which is or not.
Did you check that the file is downloaded correctly from the previous step?
Well, I get a green light, so I'm
Yeah, click on it. No, click on the on the step. Oh no, you have a wrong file. No, then you have the link wrong.
okay.
So it's not getting the right file. So it is downloading something.
But
You have to go to the edit mode. Click on it. Yeah, this is not. It should be start with raw content. So go to GitHub.
I got the wrong link, sorry.
Yeah, so probably you got the link wrong. Yeah, you got the HTML of the GitHub page. Yes, you get this link. Yeah, you're welcome. Also, this is a nice thing about it. Like, however you design it, it is reproducible. Every time you run it, if the files didn't change, you will get the same results again and again. So,
It could actually should get out.
okay, all good. So now we have this data. We need in the next step, we need now a new step. It's a transformation, another transformation step to convert this naive model into the Kimball model. And the node for that is SparkQL construct. Okay, this is where the construct comes into play. So, as we said before, very briefly, that the construct query select the data from the graph that you're applying the query to, and you can, in the construct part, retransform it any way you want, right? But first, we need to select the data. So, looking at this file here, first thing we need to define our prefixes. So one prefix could be this one that we already created, right? Or no, not this one we need, but we need the prefix for the predicates, okay? So let's just start before the construct saying prefix. I will call it predicate, and then put, with an F, this part. So I don't have to repeat to hard code this part every time I want to mention the predicate, okay? Now in the where clause, this is, I want to get all the data from the graph. So the subject is whatever, I need all the rows, right? So the subject is a variable here. And then predicate. What was the name of the first one? The row number, let's get that. Row num. And then I will call it row num, okay? On a new line, or I can do it with a comma, so it's less writing. Predicate, what is the next one? Material. Material. And then I will call it material here. Clear. Okay? All good. And then the next one, core size. I will only take one of all the physiochemical properties, because it doesn't matter, once you create the mapping once, the rest will be redundant. So here you choose what do you want to extract from the source, because sometimes you have a huge Excel sheet or CSV, not all the information are relevant. I want to construct knowledge graph from a subset of the columns, right? So I don't need to select everything in the first place. So after that, the material, I will take the core size. Let's call it core size. And then what else? Assay. Predicate. Assay. I need the species, the cell line, of course. Cell line, or call it cell line. And then the species. What else? Time and those, even though the Campbell model doesn't have those, but I will show you how to do it at least. And then we have predicate those. Here you are getting that whatever value here, it should be identical to the column name in your CSV, right? Because it was this is predicate is using the value from your column names. Yeah, absolutely. What else? One last value, the viability. Pred viability. Because now we're done, the last one will be dot, right? Let's do save changes and then go back again to edit, because if you left out of this window for whatever reason, it will gone if you didn't save it. Okay. So let's open the model. Let's start with this one. Okay. What do we need to create from this data? In order to fulfill this model, or at least we have information about the materials, the substances, right? It's in the material column, like aluminum oxide or copper oxide or whatever. So we need to create IRIs for the materials, right? And we have an assay. Every row is an assay. So we need to create IRIs for the assays. We can reuse the same one from the file because we already constructed them this way. We need to create IRIs for the activities, because every row is an assay with viability, right? So this is a measured activity. And we need to create one for the cell line. Okay? This where bind comes to work, right? So the material, the cell line, the species are just literals. Check the file here. So this is AL203. But if I want to create an IRI from it for the target model, I need the full URL. I need to reconstruct that. And the way of doing that using SparkQL is with the bind. So with the bind, I can say bind IRI concat the first value, whatever part of the URL you want to call. Let's call it. I prefer to follow the same logic we did for the rows, which are the essays. So http swat for hcls.org/tutorial. We did before essay, right? Or row maybe. We did row. So now I want to call it material. And then /, right? The second part of the concat, what will it be? Row num. Because every row is a different material. So I want to construct the URL or the IRI for the material. What distinguishes that this IRI is a material is the material word in it. Okay? So we close the concat, we close the IRI as material IRI. And the close one. And it's still maybe this one should be string. Okay, this is the concat first. Concat IRI. Okay, dot. Okay, so we constructed for every material in this RDF, in the source RDF, which captures the CSV, an IRI. So now we have access to this part of the model. Now we can link all the properties, here this one. Because now we have IRI for the substance, we can create in the construct a triple says has attribute, for example. Okay? What I will do here in the construct, we will have material IRI. Now it's the subject, right? A. What is our target model? It's Campbell. So it will be Campbell substance. You see this point? We went from a row in a CSV. We have now an entity in the target model from Campbell says this IRI is a substance. Is that clear? I will do it part by part. Let's go for the core size. Also for the core size, you need an IRI. We will use the same template, but instead of material, I will call it core size. Okay? And here I will call it core size IRI. And now, how do I do it here? The material IRI. What was the thing here? SIO 508. SIO. Let me see. SIO 1, 2, 3, 4, 5, 8. This predicate, the label of it is has attribute. So this is the predicate. And now what should I put here? Now we created the IRI of the material. We gave it a type, substance, the core size. Now we created also the IRI for the core size, and we want to link them together. This is this part of the model. We created the substance IRI. We created the property, in this case the core size, and we want to link them. So the triple is substance, has attribute, core size. This is the triple. Substance, has attribute, and then core size. Right? Before that, we need also to say what is the core size? What is this IRI? So the core size IRI is A. I'm not sure if Campbell has a property, but you can choose whatever you want. So for now, let's consider there is property in Campbell. So now we're defining that this core size IRI is a property. And we have a link between the material has attribute, this property. You get that? What else the property needs? The property IRI has value, the literal. Where is the literal here of the core size from the source graph? Here it is. It's the direct response, the direct value of the predicate. So if we go to this is the result of the tabular core size 39.7. This is the value of the core size. We constructed the IRI to be just link, right? It's the value is not in there. It is here. Is it still clear? So now, I'm walking exactly step by step here. We created the IRI of the substance. The identifier in it is the row number, because every row number is an assay and different material and different values. So, and the property IRI, we did that. We linked them together. Each one of them, we said it's a class from the model. The material is a substance and the core size is a property. We link them together. Now we are in this part. We need to assign the actual property to the core size IRI. And to do that, we say core size IRI. Then what is it? SIO 30300. 300. And then what here? core size. This is the actual value. That's enough for here. So we have now all this section. All this section already modeled from the CSV into RDF. Let's run. Let's save. Now also every step needs to link to the other. So we link the tabular to the SparkQL construct, and we debug this component. It's done. Let's check the output of this file. It's a TTL. Look, now we have a material. It's IRI we constructed. It's a substance. It has a type. It has a property, and this property is linked to the correct IRI. And the second part, this is the property IRI. It is a property, and it has a value 39.7. So we created 4 triples from that single cell. Where is now? We created 4 triple from a single cell from this row. It's the material that has a core size of 39.7. Right?
He ask you what happens when you don't have a full yield table and you have yield values. So you tend to create a whole true Dublin when you detect that
You can't.
is empty, or is he going to escape now?
I need to try that, but anyway, if we need to check that. If you have null doesn't work, you cannot have an empty subject. Subject always have to be an IRI. So that if that's the case, it will trigger an error. If it's treated as an empty string, then you will have at the end multiple materials or multiple entities having exactly the same IRI because they have empty string after the prefix, right? So that will cause also problem in your graph because you will see many attributes. One thing you can do is you can here in the construct use filter. Filter material, for example, or core size as a string. Let's say string is not empty. So it will only select the rows where the value of the core size is not an empty string. So you make sure there is value in there, right?
The problem appears before when you create a semantic side version of the CSV. Do you know if it's going to escape the triplet?
I'm not sure. Wait, I need to try that and see how it's if the triplet from the beginning is there.
Oh,
yeah, I'm sure. Yeah, this is a very basic thing, so I'm sure it's taken care of somewhere. But I didn't try it myself, to be honest. Yeah, sure. And you see here, one moment. Yeah. Okay, so we forgot to assign the substance. Actually, we created the material IRI and we called it substance, but we didn't assign the actual value. So here what we can do, usually it is in Kimball, it is in the label. So we can do RDFS label, and then it's the material itself. Okay. So now we have the RDF already for this part of the model. And when you do it in any programming language, in Python and RDF lib, for example, you're going to loop over the CSV. You're going to split by the delimiters, right? And you're going to, for each value, you're going to create, using RDF lib, create a triple. You pass the subject, you have to do that also as a template string in Python, and you have to give the value. You have to do exactly the same thing in any programming language. The checks, all these checks about null values, empty, assigning data type, here we're using SparkQL construct to do it, while in your programming language of preference, you either use the package or use the language, right? So here you're seeing that we're using SparkQL for the querying and for the constructing of the knowledge graph. and the Docker Compose will take care of the infrastructure for. So why we're eliminating all of these details of gluing the components and learning a new package, a new programming language. This was the whole idea of this approach. But the logic of thinking is not different if you're gonna do it in a programming language. But you skip many of the skills that you need to learn, and many of the tools that you need to link together. Because there you have to start your Virtuoso, you have to install the libraries in Python, you have to learn how to get the file, how to parse it, how to use the graph library in whatever language, and how to load it into Virtuoso, and how to set up the Stargle interface. Yeah, all of that is encapsulated now. And we're focusing entirely on the modeling, on the mapping from the CSV into the model. So we have this part now. Let's see the activity part. So also the activity needs an IRI. We can do the same here. Instead of the core size, we call it activity. What else do we need? So relation, the type, and the value. Okay. So now we generated the activity IRI. The first thing is to define the type. Always RDF type or A is, yeah, every resource should have a type. So here it's Campbell and activity. According to the model here, it's Campbell, activity. Activity IRI. The labels also a common practice, but since here we are constructing the graph as you want, you can put the activity whatever you want. So we can call it cell viability. Okay. And then again the activity IRI. What else we need to fulfill? The relation. The relation is a predicate in Campbell that tell you. So sometimes the assay will give you, as I said, smaller than, or bigger than, or range, or exact equal, or not equal, or so, right? So here, as you see, maybe it's too small. No, it's coming. So those are the values that the relation could take. So that's telling me this activity, which is the reading from the assay, it's exactly 90%, for example, cell viability, right? Sometimes it could be a value bigger than or value smaller than. So this is the qualifier. What is this number? So what is the relation between the readout of the assay and the number? Is it reading, or is it range, or is it a mean, for example? Okay. So the activity IRI, here we have Campbell, relation. Here it's equal, right? So the cell viability is exactly the number we have, so it's equal. Again, activity IRI, what else we have? We have the type, and we have the value. The type is cell viability, so we can also do that again. Sorry, type. Okay. And the value. What is the value here? What should I put here? So we're not going, everything happening in this query is we getting the data from the input RDF, which is the tabular results of the CSV file, and we're reshaping it. We're transforming it into a different model. So whatever we need to fill here, it should be coming from the where clause. So this is the activity. This is the readout of the assay, the value that we're getting when we apply the nanomaterial on a cell line for X amount of hours. So which one of those columns in the CSV is the value of the viability? Is the viability. Yeah, that's what I'm asking. Nobody answered. It is the viability. So this is the numerical number, viability, okay? And we have, so you see here, the cell viability, this is part of the semantics that was implicit knowledge in the CSV. We know that column is cell viability, right? But here we implicitly encoded that. And the other one is the one I'm writing now. It's Campbell units. Also, that CSV didn't contain units. You need to go back to the publication. It's a supplementary material of an article. I will show you in a bit. So you need to read the paper and say the values were gathered in nanometers or percentage or something. Here we're encoding this value in the graph. So it was percent. I've seen before in one of the queries they have prefixed. I'm not sure which one. There is unit ontology. I'm gonna claim now it's this one, okay? Let's say it's unit like this. Let's call it unit. There is a URL for the units, but I don't know it by heart now. So now we have a unit. It's a class called percent. So we know this value is this value of viability is of a unit percent. It represents cell viability, and it's linked to this nanomaterial of this core size. Now we have all this part of the model here. The Campbell activity, we have all of this, and we have all of that with a substance. So now what we can say from this part of the model, we have an activity of an exact value of type cell viability of a value, let's see, for example, 90%, so it is of unit percent, and this is a result of a treatment with the substance aluminum oxide, Al2O3, that has a core size 39.7 nanometer, right? All of that knowledge now is there, but it's not easy to infer the same thing from the, it's not available at all if you don't know the actual experiment. Actually now, which makes me, we forgot also to put here the core size. We didn't put also units. So we could do the same thing, core size. Or the core size units, you can say nanometer. So now the nanometer and percent are, I made them up, but I will let you know how do you find, so there is ontology lookup service. It's OLS. It's a resource also maintained by the API. It's, you search for whatever. If I want to look for percent class to tag my my values with it, I look for percent. Okay, I design percentiles. It's not what I want. Percent, for example. Percent, this is from the unit ontology. This unit ontology is the most comprehensive one and updated ontology, right? So I want to use it from the unit ontology. I copy this URI. This is the full URI of the unit percent. And I go here to my data. First thing I do, if it's new, I don't have it before. I already have it, the UO. I will put the prefix. All of that is a prefix. I only need to take this part, okay? So now the UO is correct. And let me go to the percent here. This. Now I have a real class called percent from the unit ontology, annotating my viability value. The same we do for the nanometer. So let's go back, search for nanometer. A big part of converting datasets to RDF is the annotation. So all these cell names, all these organisms should be mapped to taxons from NCBI. So human is 9606. Cell lines have their own classes. Materials have their own classes, right? So the whole part, if you want to make it really semantically correct and reusable and interoperable, all these details. A life sciences dataset, experimental dataset that contains a numerical column without a unit is useless, right? If it contains a cell experiment without cell line mentioning the cell line, it's useless. You need all this information to be there, and that's why semantic web will help us with this. Nanometer, you see here, nanometer from a unit ontology. Okay, perfect. Now we already added the prefix, so we only need to copy the actual part of it. So nanometer here, right? Okay. So now we have full part. I can say the entire model from here, activity to the property is mapped. Now let's move to, okay, how much is the time?
48.
The document. I'm gonna tackle the document now because it's different. Okay. So this part of the query, I'm gonna rename it, and let's call SparkQL construct of assay data, or for substance, and what was the other activity, right? But I want also to have a mapping to create. I don't know.
Can you maybe paste the query?
Oh yeah, that's a good idea. Where is it? Now I want SparkQL construct for the document, and this information doesn't exist in the CSV at all, right? We have this file as a supplementary material of a paper, but we don't have the actual information inside. Let me see. I'm gonna I'm gonna reuse the query I had before. I'm gonna show you now. So here we need to create this document part, right? Because this entire data set, the data.csv, is coming from a publication, and we need to present that publication, this provenance information, in the RDF. In our case, we can construct that. You already know the DOI of the paper, you know the title, you know the year of the publication, and so on. So all what you need to do is to encode this information here. So we created an IRI for the document. It's a SWOT for hcls.org/tutorial/document. Okay, this is the IRI of the document. We give it the type document, and as we see in the model, the document links to an assay, to activity, and to substance. So we have has assay, has molecule, has activity, right? And we link them to the IRIs. In this part of the where clause, we don't need to reselect everything back, because all of those columns, we don't need them. You only need the material and the assay and the activity, right? So only select those, and we create the IRIs in the same way, and we link them to the document. What we need to add here to this document, let's look at the model. We have document type, right? So we have Campbell document type. We know already it's a publication. So the values are book, dataset, publication, patent. We know it's coming from a paper, so here it will be publication. All of this knowledge that was implicit, we're now making it explicit in the RDF model. What else? The date. Let me see, check, just to get the DOI. This is the DOI. So this is the original paper where this data is coming from. It's published in 2018. So the date here, Campbell, date, and we see in the model the Campbell date is an integer. So it has to be an integer value. So it's a 2018. How do I make this an integer? Hat XSD integer. So now also we hard-coded, or we explicitly mentioned the date of the publication, and we annotated that with an integer. And then we also have the title. Everything without a type is considered a string. So if you do not mention XSD date or integer or something, it is a string. So Campbell title. Okay, we have the paper here. We copy the title of the paper. We put the title here, and okay, we have the title. What else? DOI. DOI. The way Campbell stored the DOI, it doesn't include the full URL, right? It only contains this part. So if I'm gonna stick literally with what Campbell is doing, I should do it as a string like this. So this part, save changes. Let's just test it. Look at the file output. I have a document of type document. It has an essay. It has 1, 2, 3, 4. It have 11 essays, which is right because the publication, all the rows of the CSV are coming from the same publication. So that document should be linking to 11 essays, which are the number of rows in our CSV file. The same for the molecules, the same for the activities. Each one of them is 11. And then it has a document type publication, a date 2018. You see that the type is integer correctly, and the title is mentioned, and the DOI is here. We reproduced the exact model of the Campbell CSV exactly as they are representing their activity data, but with SparkQL construct queries from an input CSV. And you need to continue the same way into the source, the essay, the cell line. We have the cell line coming from the where clause, right? Here. The cell line is already here, and the species are already here. So we, in the same way, we create IRIs for them, and we link them to the correct class. If we don't know the class, we go to the OLS, the ontology lookup service. For example, if you want a human or Homo sapien, let's see, why not Homo sapiens? What? No, this one, yeah. Homo sapiens, it's from the NCBI taxon. This is the ontology for the taxonomies for the organisms. And this is the IRI of it. Okay? I'm not gonna add it now, but anytime you find a new prefix, you do prefix, NCBI, you put that, you just take the part that is changing, and in your whatever you see, organism, IRI, A, NCBI, and you have a link, and you need to continue. Once you have this model, if you have 10 data sets with the same structure, it will be, you don't need to rewrite the queries. You just change the URL and you convert them into RDF. Okay? So this is the modeling part. One little bit I can do, let's see. I want to show just RDF to file. So now another step for conversion, right, is to get this graph. So this is already a graph. You see, it's a turtle. It's all these triples. I want to make them into file, and I want to load that into Virtuoso, the local Virtuoso that I'm running. And I will show you that example from here to save time. From the pipeline I already made. So the pipeline is already on Slack. You can reuse it. It has all the steps in there. So RDF to file, and then this is the step that load that RDF into Virtuoso. It's called the graph store protocol. These values are fixed. Since we're using Docker Compose, the URL with the port, with the path, it will always be the same. If you're using the same Docker Compose, you just need to copy these values, right? And when you do that, this entire graph will be loaded. If I running, this is the pipeline that I made. It's already green. Let's go to localhost 8088, and let's search, for example, which query you want. I did the query for the essay label. I don't know if this one will. This one we don't need. Okay, I didn't have units. No, I don't need all of this. I just need 3 of those. So we have essay, have molecule. Let me see if we have data. No data at all. Campbell, let's start with the basic one. This is the data that you see. This is the local query interface. And this is querying also the local Sparkle endpoint. So those are the essays that are inside the Virtuoso installation, and it's which came from the this pipeline. Okay, so at the end of this pipeline, all this construct queries resulted in RDF file. That RDF file was stored into the local Virtuoso, and if I switch the query interface and start checking, give me all the essays in there, it will give me all the essays in there, right? Usually all these steps, each one of them has its own set of instructions to set up and link, and with a single pipeline and the Docker Compose, it saved a lot of time already. I'm not saying it doesn't require knowledge and it doesn't require work, but at least you're focused on the annotation and the modeling of the data, and not on all the technical and programming skills required for that. And the Sparkle constructs, you need to replicate that logic anyway in any programming language, but you avoid all that details of tools, integration, setup, programming around it.
How does it compare with branch fields?
With what?
Branch fields, where you can merge the ontology with data sets.
It's the same here. You can load the same way. You can load the ontology in the knowledge with the Virtuoso installation and have them both together. The same way. But you don't need to do transformation because you only do HTTP GET. The ontology doesn't need transformation, and you load it directly to the graph protocol. So you can load or merge the ontology with the output dataset. It does.
I think void fields allows you to do this, the annotation of data with the ontology, right? Yeah. So where you use the OLS right now to look up terms.
Okay. It annotation. It supports the annotation part.
Ontology, which is correct, then you can use that as well the framework for the data.
Okay.
Within the data. And then you got it.
Yeah. Yes. Yeah.
With it from the data into
Yeah, that's possible. But you need also the model fully there. You need all the predicate, all the classes in there. Yeah. The annotation part will take some work anyway.
So what if the unit is encoded as a literal? How does this convert?
In SparkQL values, you can map. If it's this, map it to this IRI. If it's that string, map it to that IRI. Yeah, SparkQL is really capable language, so you can do all these transformations, many of the things of transformation. Check if it's literal of this value, then you map it to an IRI. You can do that, right?
Can you create your own component or?
You can define templates. So if you have some specific values that you need to reuse, you can do that. And if you need to create your own components, you need to fork it's open source project. So you need to fork it and add it programmatically to appear here, but not visually, no. And the entire pipeline can be exported. So you can export it and import it in one instance. So if you developed it locally, you can export the pipeline, load it on your server, and run it and feed a live SparkQL endpoint with it. Can you brief me on your impression on the whole process? How did you expect it to be, and what is your impression after you've seen it? Did you expect it to be less easier than this? Or did you try other approaches and you find it easier? Going all the way from flat file into endpoint, not just doing one step easier, but the entire thing. How do you compare that with your own experiences?
Yeah, here you still need some decent Sparkle.
Yes, yeah, but it's the only programming skill you need in this whole process, or even Sorry? I've used that too.
What's better most if I use for
RTML, you need to write all the mappings. You need the RML mapper, Java. You need Java installed. You need a lot of tools to be hooked together. Yeah, and that takes a lot of time and a lot of errors. Debugging is not easy. Yeah.
this is what's better about?
I did that. I used the ER RML. It's the YAML extension. Yeah, but it's way more time consuming than this.
Is it maintained well?
I checked GitHub. They are regularly pushing. It's a group in Austria.
Think it and because sometimes developers.
Absolutely, I agree. Yeah, that's the thing. Let me see if there are citations. The following groups. Oh, okay. Yeah, it's several. It's collaboration, but it's mainly in Prague, in the Czech Republic, with someone from Charles University. I think this is Sweden, right? Oh no, it's also Czech Republic. So it's in Czech Republic, not Austria. But it's been around. Let me see. So 2 months ago was the last one, and they have, this release 2022, 2,000 commits, but I don't know how old is it actually. It's one way of doing it. Depends on your use cases. It could be the way, or even it depends how. Sometimes you have already an infrastructure and you need one component to add to it, then this doesn't fit, right? If you are maybe have a pipeline using Galaxy or Nime and you want small script that uses R2RML, for example, that could be more convenient. If you wanna start with doing infrastructure or the whole thing, maybe this will help because you focus more onto the mapping, or so it depends. I don't know.
Very open refine.
Yeah, I've seen that.
Yeah, and your manipulations there, maybe.
And yeah, when you take up,
I'm like,
and that But you need also to not to forget getting the files, loading them into the Sparkle. I don't know if they do that. Yeah.
So how scalable was this?
All these nodes, they have a chunked version of it. And the chunked version you can do with limit of set. So no matter how big the set, you can go them iteratively. Or if you have a log file, you can go over it in a chunked way. But I don't know how big actually. Because also it depends on your memory of your server, right? If you're gonna process 10 gigabytes data and you have only 4 gigabyte memory, also that will be. But for the processing, they have the chunked versions of the nodes, and those can work scale up very well, especially with remote Sparkle endpoints, because the timeouts there are the bottleneck, right? So
one last question. So very often in data like this, you have one in essays then test for a lot of compounds.
yeah.
So you gave everything IRIs based on the row number. So you get more resources than there probably are really essays.
The reason is Kimball only save one time and concentration. It doesn't have a series of concentrations per assay. They call it the active concentration. So they have for every molecule a single assay. But you can
To have, okay, but you mean you don't know if they're the same.
Yeah, but and in Kimball there is one assay that contains multiple compounds. That's you need to take care of here. Either you add a column to the CSV beforehand to group the assays, right? And then you have the materials on them. Also in SparkQL you have hash MD5 function or SHA-1. You can group a couple of fields in a string and hash it. I used that before. And then you make sure you have the unique.
So there's works for me as well, but with other tools.
Yeah.
It is your data develop is contained in what is files of one at least another, not like risk database ID. In that case, did you just or five?
They will automatically link, right? If you generate the right IRIs, you're putting them into the graph, automatically they will link. So if you're using, so you have foreign key, primary key, right? If you generate IRI based on the primary key and you put it in the graph, and then you generate it from the second file using the same foreign key as for IRI, they will automatically link because the subject will be the same, right? So that's here the graph is nice, the only one version of the data because the IRI is unique and everything else will link to it.